Hi everyone. So as I mentioned, I'm going to be uploading this video to help you review the material that we would have covered in class on Tuesday. So I'm going to start the notes by asking you to think about what the last thing we talked about on Friday was. So remember, we mentioned that there's two ways to think about annuities. You can either think about it as chronologically, or you can think about it from the bucket approach. And remember, I kept repeating last week that the bucket approach is the way that we eventually come to a formula for solving for the future value of an ordinary annuity. We're going to do that a little bit later on in the notes for today, but just to give you an idea, again, there were two different ways to approach looking at what an annuity is and how to calculate the future value of an ordinary annuity. So what are the similarities and differences? Well, think about them as being similar in the sense that they're both talking about annuities, but they're different in the sense that the chronological approach sort of looks at an annuity and a future value of an annuity as a running balance. And so remember, we filled out that table that you also had to do for homework. That was a running balance, and so you consider each year 1 year at a time. So consider the deposits just 1 year at a time. Okay. Whereas in the bucket approach, again, we also filled out a table for that, and it was also part of your homework for the weekend. In the bucket approach, you look at all the deposits simultaneously, but notice that each of them is collecting interest for different amounts of time. So each deposit had a different exponent that represented what the amount of interest was in terms of how many years it sat there collecting interest. So I'm just going to write that it collects interest differently. So really quickly, I'm just going to flash those tables just to give you a reminder again about what we did on Friday. I'm going to zoom in for a second. Again, this was on your homework for Friday, not for Friday, sorry. This was your homework that was due this past weekend. So notice that the chronological approach is having you calculate just year to year to year. What is your starting balance? What is your ending balance? Remember that in the following year, you start with the balance from the previous year. So year 3, we're starting with this year 2 ending balance, and we continue from there. Now with the bucket approach, it's a little bit different. Again, we said you consider all the deposits at once, so here it was 4 deposits of $2,000 each, but you notice that each deposit collects interest for a different amount of time. Now, even though there are 4 payments being made, notice that the exponent for the first payment, we said will only collect interest for 3 years. Again, the exponent is 3, because we said these deposits are being made at the end of each year. And so by doing that, you're losing out a chance to collect interest. So we noticed a lot of these patterns on Friday, and again, that's what we're looking at now when we're considering what are the differences between the chronological and the bucket approach. Every once in a while, we'll come across an example that doesn't really talk about money, but can still be thought of as a compound interest example. And so for these same numbers, again, suppose that we're looking at 2,000, 6.3% compounded annually for 5 years. How could we consider this in terms of population? So for the bucket approach, if you're looking at this in terms of population, you would be considering what happens when 2,000 residents move in each year for 5 years into a city, let's say, and each year the city grows by 6.3%. The city's population grows by 6.3%. So in the bucket approach, you look at all 2,000 residents that are moving it in yearly. Each growing by 6.3%. But remember that it is the amount of time that is different for each of these groups of 2,000 residents. So the very first group of 2,000 residents that moves in grows by 6.3% for 4 years. The next group of 2,000 residents moving in will also grow by 6.3%, but only for 3 years, and so on. Whereas in the chronological approach for the population, we would be looking at each group of 2,000 residents in 1 year at a time. So each group of 2,000 residents moving in 1 year at a time. And again, remember that we say that the chronological approach is really like this rolling balance. You look at the first 2,000 residents move in, grow 6.3% the following year, and then you also add another group of 2,000 residents, so on and so forth. So chronological and bucket approach are just two ways to look at annuities. We really will be focusing more on the bucket approach because we said that that's where our formula is going to come from. So our job for today is going to be to actually see where the formula comes from. So to do that, let's take a look at again the same example, $2,000. End of each year, account is giving you 6.3% compounded annually. What would the number sentence for the bucket approach look like if you kept investing $2,000 per year for the next 20 years? So think about that for a second. If we had to write out the really long number sentence, almost like what we did in class when we made our own annuity up, and we said, okay, you deposit $100 a year, each collects interest for a different amount of time, and we wrote all those sums on the board and then we added them together. So think about doing that this time for 2,000, end of each year, 6.3% for the next 20 years. Remember, we noticed that the very first deposit will collect 6.3% for 19 years. You should be asking yourself, why 19? Whoops, I was going to write out 1 plus 0.063, but I guess we can just skip a step and we'll put 1.063. 18 years, year 3 rolls around, you made a $2,000 deposit, it collected 6.3% for 17 years, and this is just going to keep going and going. So we're not going to write out all 20 terms. We're going to skip a few steps, and that's what's being denoted by the ... Then when you get towards the end, you start to see that, okay, 2,000, 6.3%. By the time you get to the 19th out of the 20th year, remember we said that one's only going to collect interest not in year 19, but only in year 20, so the exponent is 1. And then finally, year 20 rolls around, you make your last $2,000 deposit. It, unfortunately, will not collect any interest. Keeping in mind, again, that this is an ordinary annuity, so that's telling us that these deposits are made at the end of each year. So again, some things to notice, even though, yes, it is for 20 years, your highest exponent is 1 less than the number of years. And every year after that decreases by 1, and you just keep going until you get to the last few where you notice that the exponents go all the way down to 0. So this is how you would write the sum. This is the sum of the future value of this annuity. So if you actually had your calculator out, I want to turn on mine just in case, but you could sum up these individual future values and get the total future value of this annuity. So we don't have to do that for this question. I just wanted you to write out what the number sentence would look like. What would change about your number sentence? Now, if we look at part B, which says, what if the amount of each payment was going to be $3,000 instead of $2,000? What would change about your number sentence that's in blue up above? Take a minute to think about what would change. Would the exponents change? Would the interest change? Or would your payments amounts change? So I'm underlining that right now, and you can see that, yes, that is exactly what's going to change. So it's going to be $3,000. I'm going to keep in blue what's the same, just for emphasis, to show that what's changing is just that deposit growing by 6.3%. So the amount of the deposit changes, but nothing else changes. Just going to rewrite the name, same number sentence. And so on and so forth. Almost there. 16th power, skip a few because we don't feel like writing all of them out. So obviously, well, not obviously, maybe I should ask you, what will happen to this future value if your deposits are larger than they were? So you went from $2,000 to $3,000 in deposits. What's going to happen to your future value? Should we think about that for a little bit while I finish writing this? I'm going to try to squeeze it in there at the end. 0.063 exponent of 0. So this future value would be larger than the future value we just calculated in part A because our deposits are larger as well. Again, we didn't calculate the actual future value, but if you had a calculator, plugged it in, you'd be able to tell that's definitely going to be much larger. Now remember, we have a way to predict about how large this annuity future value should reach, because if we're making 20 deposits of $3,000 each, you should have at least how much money? 20 deposits of $3,000 each. That's $60,000. Now you're going to have a little bit more than $60,000 because remember, each of these deposits collects interest. So your contribution was 20 deposits of $3,000 each for at least $60,000. Compare that to part A, which was 20 deposits. What in the world? 20 deposits of $2,000 each, which would have been only $40,000. So just by increasing your deposits by $1,000, you're going to have $20,000 more over those 20 years. So now we want to go towards a formula for the future value of an ordinary annuity. I apologize that the title of that page went on to 2 pages. At the bottom of the last page, towards a formula for the future value of an ordinary annuity. Now we want to derive the formula of the future value of an ordinary annuity. So I'm going to ask you to pay attention to what it I'm going to specify that. I'm going to demonstrate that a little bit more below, but just to have you think about, how do we get the formula from these really long number sentences? Remember, we said, why would you want to sit there and write out all of these different payments and then try to add them together? We don't want to do that. So we want a formula. So to make the derivation of the formula a little bit easier, we're going to make our deposits smaller. So let's pretend that our deposits are going to be $1 a year. So again, not a lot of money. We're just going to try to simplify the math as much as we can. Let's keep 6.3% for 10 years. So notice what the number sentence looks like. So take a minute, take a look at this number sentence here. So we've got our 10 deposits. First exponent is 9, last exponent is 0. Again, I skipped a few steps, but there would be a total of 10 deposits shown in this really long number sentence. Right now you can only see 7 of them, but the other 3 are there. Remember that little dot 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 there is showing those extra deposits that we don't feel like writing out. So again, make sure you understand why the exponent is just 9 for the first one. We said that this is because it's an ordinary annuity. So each deposit is losing out on a chance to collect interest, including that last one, which has no interest. So to derive the formula for the future value of an ordinary annuity, we're going to do a little bit of algebra, and that's what I have highlighted in yellow. And I'm going to change the color so we can look at it again. I'm going to highlight it in blue. So the first thing we're going to do is we're going to multiply both sides of this number sentence that you see by a growth factor, which I'm going to highlight, of 1.063. So imagine what's going to happen to this number sentence in blue, that I'm highlighting one more time, if you were to multiply each of these terms by an extra growth factor. What would each new term look like? So I'm going to write that down in the space that's sort of below here. Whoa, what a mess. That space there, I'm going to write down what each of the terms would look like. Now again, I'm going to skip a few of the terms because I clearly don't have enough space to write all of them, but I want you to think about what multiplying by that extra growth factor of 1.063 will do to each of those terms on the other side of the equal sign. For example, the very first term, actually, you know what? I'm going to show you on a clear page first and then I'll go back here. I'm going to insert to blank page. Okay, we said what would happen. So here is your very first term. It was 1.063 to the 9th power. What's going to happen to this when we multiply by another 1.063? So what's going to change is the exponent. Remember, a little bit of algebra. So when you take 1.063 to the 9th power, multiply by another 1.063 to the first power, we add the exponents, same base, add the exponents, and so we get an exponent of 10. Now you're going to multiply all of these terms, I'm just going to go back for a second, you're multiplying all of these terms by an extra growth factor of 1.063, so each of them will have a new exponent that is increased by 1. So $1, 1.063 to the 9th. $1, I'm going to try squeezing it as much as I can, 1.063 to the 8th. We skipped a few, dot, dot, dot. $1, 1.063, that is now to the 4th power. $1, 1.063 to the 3rd power. $1, 1.063 to the 2nd power, and even that last term, which I'm going to highlight in a different color, so even this last term here will be multiplied by 1.063. I'm just going to squeeze it down here because I don't have enough space. So even that last term will get multiplied by 1.063. Okay. So we just completed the first part of this clever idea where we multiplied both sides of the equation by 1.063. Now we want to do the second part, which is to subtract the original equation from the new equation we just wrote in blue. And what happens when you subtract these two number sentences? What terms, should be subtraction, what terms do you notice are going to subtract to 0 when you combine them? So think about that for a second. What terms will subtract to 0 when you perform the subtraction, when you actually do that? So looking at the number sentence in blue minus the number sentence that was already written, the original, what terms are going to, I don't want to say disappear because they don't disappear, they just equal 0 when you subtract them. Which terms will equal 0 when you subtract them? So it turns out that this very first term in the original number sentence to the 9th power, when subtracted by this term to the 9th power, will equal 0. This term subtracted by this term will equal 0, and every other term that has a matching pair will also subtract to 0. So again, imagine you did this for all of the terms that had a pair. all of the terms that had a pair. What is going to end up happening is that you will have one term left over from the new number sentence that had nothing to subtract it to, and you will have one term from the old number sentence that also has nothing to subtract it to. We're going to also subtract the right-hand side of the equal sign, so that's 1.063 future value times, subtracted by that future value. So let's write out what we have. Okay, so we have $1, 1.063 to the 10th minus $1. That's what was left over from the old number sentence, equals 1.063 FV minus FV. So we wrote what was left over on the left-hand side of the equal sign after all of our cancellations and subtractions, and we wrote what was left over on the right-hand side after all of our cancellations. Now we want to solve for future value. So on the right-hand side, we want to end up with this, but right now we have a few things to clean up. So what can we factor out, clean up, use a little bit of algebra to help us do this? I'll just erase this for a second to give me a little bit more space. So we're going to factor out $1 from both of the terms on the left-hand side. So by doing that, we will be left with, I'm just going to put in different kinds of parentheses here, 1.063 to the 10th power minus 1. We factored out $1. Right-hand side, we're going to factor out the future value. So we'll be left with 1.063 minus what? 1.063 minus 1, which is just 0.063. 1.063 to the 10th minus 1. Okay. And our last step to solve for the future values, we're going to divide both sides by 0.063 because we want to just solve for the future values, so we don't want to, sorry, I don't know what that is. We want to solve for future values, so doing so, we get that the future value is equal to the following. The payment amount, $1, 1.063 to the 10th minus 1 divided by 0.063. Okay, so the payment amount was $1. We deposited $1 each year for 10 years. Let it grow for 6.3%, those 10 years, 10 deposits. And that was the future value of this annuity. Now, a lot of algebra just happened, so make sure that you go back and review what happened up here first. So we took the number sentence for the future value of an ordinary annuity, we multiplied it by a growth factor of 1.063, we wrote out our new number sentence, then we subtracted the two number sentences, we noticed what equals 0 when we subtracted, we crossed those out, we wrote what was left over, and then we simplified to solve for the future value. This is something that's going to be really important for you to understand because it will come back again. If not on the second exam, definitely on the final. So what I'm going to do is I want to rewrite this expression down at the bottom because we actually want to solve and see what this is equal to. But also we want to write a general form of this formula that's going to help us for any annuity. This is just an example of one annuity, but we want to be able to use this formula for any annuity, so we're going to talk about some variables next. I had a blank page here. Let me just zoom out for a second and move this stuff out of the way. just want to move it up on this page because I want to give myself some space. Okay, to just write out what we did with the formula. So we were left with the following. We had $1 was the payment amount. We had 1.063 to the 10th minus 1 divided by 0.063, and we said that that equaled the future value of this annuity. Now you can plug this into your calculator and find out what the actual future value is in dollar amounts. What we want to do is label what we're noticing can be used for any annuity. For example, we said this was the payment amount. So for in any annuity, remember we said that one thing that makes something an annuity is that it has to be regular, equal payments. So the payments here were $1. Notice that inside the parentheses, you have 1.063 to the 10th power, so that represents your growth factor. You're subtracting 1 from it, and then you're dividing by the interest as a decimal. So to write that out, we are taking our growth factor, we're subtracting 1 from it, and we're dividing by the interest. And that is the future value of any ordinary annuity. If you take the payments and you multiply them by this growth factor minus 1 divided by I, you will get the future value of an ordinary annuity. Now just to label some things, this number inside the brackets here has a special name, which is called an annuity factor. And in your textbooks, they label it S sub n of I. Whoops. Why did I just use brackets? I meant to use parentheses. So this annuity factor, S sub n of I, describes one number that you can multiply your payments by to figure out what the future value of an ordinary annuity is. Again, n represents your exponent, I represents your interest rate. So we should be able to find the annuity factor for any annuity, as long as we know what n and I are equal to. So in this case, find the annuity factor for an ordinary annuity which payments are made annually, 15 years, so n equals 15, 4.5%, I equals 0.045. So what would be S sub n is 15 of I, 0.045. Well, that's going to be our growth factor minus 1 divided by the interest. Just going to make that a little bit smaller because I exaggerated a little bit. So go ahead and simplify this on your calculators. What is the annuity factor for this annuity? You're going to hear me typing away. Now be really careful about order of operations on your calculator when you're plugging this in, because you want to make sure that you are correctly interpreting that there is a numerator, growth factor minus 1, 1.045 to the 15th power, minus 1, not the exponent minus 1, but the entire growth factor minus 1, and that's being divided by 0.045. Okay, so your growth, actually your annuity factor comes out to be 20.78405.429. So you can calculate the annuity factor for any annuity, as long as you know what n and I are equal to. So what is the annuity factor for a 5-year annuity? 6.3%. This is relating back to our question. Remember we said 5 years, 6.3%. This was way back in the beginning. What would have been the annuity factor of that? We would have growth factor minus 1 divided by the interest rate. growth factor minus 1 divided by the interest rate. Let's see. I got 5.670955988. Let's use that to compute the future value of 2000 at 6.3%. Remember, this was the first example we talked about at the beginning of these notes. So now the future value of $2,000 growing at 6.3%. 5 years. Let's see if we get the same number we got when we computed this earlier. Does anybody remember what we got? Let me just scroll back for a second. From the notes from Tuesday. I remember that. These are from the notes from Tuesday. So, whoops. I thought I had it on these notes. Notes from Tuesday. Let me scroll back 1 second. Notes from Tuesday. Sorry, not Tuesday. Last Friday. 6.3% for 5 years. Let's see if the formula gives us $11,341.91. These are the notes from last Friday. Remember the ones I uploaded that I said I was going to do a different example than the one you had for homework. Alright, so let's see. Let's go back to our notes. Do we get $11,341.91? I hope so. This is FV 2000 times 5.670955988, and that is okay, $11,341.91. So we did get the same thing. Awesome. Alright, so a couple more examples to get us familiar with using the formula. And then we're going to talk about compounding frequencies. So, really quickly, Donnie decided to invest $5,500 each year in an account that she expects to earn 8.25%. She keeps this up for 35 years. How much would she end up with in her account? So we want to know what the future value of $5,500 in payments a year, 8.25%, 35 years, growth factor minus 1, divided by the interest rate. Again, interest rate as a decimal. So this is probably going to be a lot of money. These sound, again, $5,500 for 35 years. That is $192,500. So she's going to have definitely at least $192,500. But anyway, let's figure out this growth factor. Minus 1, and we're dividing by 8.25% as a decimal. So this is a growth factor of 182.201126, and that's what's being multiplied by $5,500. Whoa. That sounds like a lot of money. That is going to be $1,2,106.19. Wait a minute, is that correct? I'm going to double check that number one more time. That's to the 35th power minus 1. And then divided by 0.0825. Yep, that's the correct growth factor times 5,500. Wow, $1,002,106.19. That is a lot of money she will have after 35 years. What if she was only able to earn 3.75 interest on this investment? What would change about your calculation? Well, we'd have to change the interest rate here and here. So would she have more money or less money? Unfortunately, she's going to have less because she's investing same amount, but at a lower interest rate. So 0.0375, 35 years. Again, growth factor -1. And she will have, what is this growth factor? Okay, so growth factor is 70. Still a large number, but not as large as it was in part A. 0613867. Alright, times $5,500 is still a lot of money. Whoops, sorry, I didn't mean to scroll. So that's going to be a future value of $385,337.59. So smaller interest rate, smaller future value, but still more money than I guess she would have had on her own. Okay, and just briefly I'm going to present a population example before we get to more compounding frequencies. And the reason for that is, again, as we said in the beginning when we were talking about chronological versus bucket approach, where we said that you can think of any of these annuity examples as population examples. So here's a good one. Now, what I want you to pay attention to in this example is that there are two things happening. I'm going to highlight those two things, different colors. So the first thing I'm going to highlight in purple is that there are already 100,000 residents living in this city. Okay, so keep that in mind, that there's already people who lived here. And we anticipate that over the next 7 years, 4,000 new residents will move in each year. So that's the next 7 years. Population will grow at a 2% per year rate. This is ignoring, details about births and deaths. We're just going to assume a steady rate of 2% per year increase. So how do we calculate the total population of this city when there are two sort of different populations growing at 2% at the same time? You've got the original 100,000 residents, and you've got these 4,000 new coming in every year. So keep track of these two by calculating them separately. When you want to know what the population growth will be, what that 2% will do to the 100,000 residents that already live there, that's just a regular future value question. That's not an annuity. We're not going to assume that there's 100,000 people moving in every year. Those 100,000 people were already there, so you've got one lump sum growing at 2% for 7 years. Add to that the annuity part. So the annuity part is 4,000 residents every year for the next 7 years. So population examples that involve two sets of people growing at 2%, in this case 2% a year for the next 7 years, requires two separate calculations, but you're going to add those two separate calculations together. So again, on the left hand side we've got the 100,000 residents that were already living there, growing at 2% for 7 years. This is going to be 114,868. And I'm not going to round this yet, even though we are talking about people. I'm just going to leave it at 114,868 and 57 hundredths. So we're going to add to that the annuity part, which is the 4,000 residents every year. I'm going to write out that growth factor. So, sorry, the annuity factor. I'm going to write out the annuity factor. So 2% growth factor to the 7th power minus 1, and we're going to divide that by 2%. It's going to be 7.434283382. For a total of 29,737, and again rounding the nearest hundredth, 13/100ths. So these are the two numbers that we're going to add together to get our total population. 29,737 and 13/100ths added to 114,868 and 57/100ths. This is, so this is going to be equal to 144,605.7, which now we can round up since we're talking about people. So this is approximately 144,606 people. Residents, citizens, whatever you want to label it, but they're people. Okay, so in population examples where you have these sort of two things happening at the same time, calculate it as two separate things and then add them together. The existing population, not an annuity because it's not 100,000 every year growing at 2% for 7 years. They were already there. Added to the annuity, which is the 4,000 new residents moving in each year, growing at 2% for 7 years. Two separate kinds of things happening, but altogether your total population would be the combination of these two. Okay. Last topic. Last couple pages we'll be dealing with the last topic, and the last topic is not new. It's just taking a look at our future value ordinary annuity formula when we have to account for the fact that we have more frequent compounding. Remember, we saw this with regular compound interest. Okay, so I'm just going to put a blank page up briefly. Again, really quick, just put up a blank page that when we had more frequent compounding in our regular compound interest formula, what parts needed to be compounded? Think about that for a second. When we had more frequent compounding, for example, suppose monthly or weekly or daily compounding, where did that show up in your formula? So we had to be careful in two different spots in our formula that there was more frequent compounding, in the exponent and in the interest rate. The same is going to be true when you look at your ordinary annuity, future value and ordinary annuity formula. When you're going to change the compounding frequency, you have to be careful in 1, 2, 3 spots in your formula. Remember, the interest rate gets divided by the compounding frequency. I'm just going to abbreviate. Whereas n gets multiplied, your exponent gets multiplied by the compounding frequency. So if our compounding frequency was weekly, for example, I would be divided by 52 and would be multiplied by 52. It's just that there's 3 different spots in your formula where that's happening. So I'm going to skip the question that says, could you write out a bucket method expression? I'm sure you could. Just keep in mind that a 6-year, just keep in mind that for a 6-year annuity that is going to be compounded quarterly. How many quarters are there in 6 years? There are 24 quarters. So that changes what numbers you're using in your formula. If I had you write out a bucket method expression for this annuity, you would have 24 different deposits of 500 every quarter. Also keep in mind that that 6.3% is not actually 6.3%, right? Because if this is now going to be measured quarterly, you would have to compound 6.3% quarterly as well. So really need to be careful about compounding frequencies changing, because that's going to affect your formula in a few different spots. Okay, so let's take a look. Could you write out the bucket method expression? Well, you don't have to write out the whole thing, but again, it would be $500 payments, 24 quarters, but remember that the very first quarter, you do not collect any interest, so the exponent for the first would be 23. We said there were 24 total quarters, but it would be 23.063 quarterly for the next 22 quarters, so on and so forth. But the same things are going to be true about this bucket approach number sentence. Remember that the last few deposits, quarterly deposits, in this case, sorry, these are not deposits, you're borrowing 500 every quarter. So the payments are 500 here. Okay, last view would just be 500 growing at 6.3% compounded quarterly for 1 quarter, 500 growing at 6.3% compounded quarterly for no quarters. Find the future value of your debt after 6 years. Thankfully, we have our formula now, so we're not going to go through writing out all of these separate future values and adding them together. So the future value of your debt after 6 years is the result of, again, quarterly compounding. So this is, I'm going to write this out the long way, but you've already calculated some of these numbers. Don't forget to compound the denominator as well, because that's also the interest rate. So what is this future value? I'm just going to write out what this annuity factor is here. So add 1 to the 24th minus 1. Should get a growth factor of about 28, almost 29. This is, I got $14,446.67. Now, interesting question. How much of this debt is interest? Well, if you borrowed $500 a quarter for 24 quarters, how much money would that be? That is $12,000. But the future value you just figured out was not $12,000. It was actually $14,446.67. So where's this extra money coming from? Remember we said that that is your interest. So to figure out how much interest is included in this debt, we would take the total future value, $446.67, and subtract the total of those payments. In this case, it's not payments, it's you're borrowing $500 every quarter, but we still call them payments. That is your interest. So that's $2,446.67 in interest during those 6 years of borrowing $500 quarterly. Okay. A couple more examples. Just in the interest of time, and so that the video is not any longer, I'm sure you're probably like, okay, I've seen enough. I'm going to include this as part of the annotated notes, but I'm not going to go through it in the video. I do want you to keep in mind, though, that now you can calculate various different future values of ordinary annuities. Remember, these are still ordinary, meaning we're making payments at the end of every term. So end of the year, end of the quarter. This one's going to be end of each month. Okay, and it actually says it in the problem. And so we're still considering just payments made at the end of every month, but now we got to take into account any compounding frequency that may be happening. So yes, this says if this continues for 18 years and the account earns 4.8% annual interest compounded monthly, just make sure that you're compounding monthly everywhere. So for n, it's not just 18, it's how many months there are in 18 years. Okay. For I, sorry, let me just rewrite that 6. So for I, it's not just 4.8%, that 4.8% is being compounded monthly. So just keep that in mind when you are calculating. Okay, so hopefully these have been a few examples to give you a sense of what the